This is Lecture 1 of Module 6 in the book Problem Solving Guide for Mechanics and Thermodynamics, Conservation of Momentum, One-Dimensional Collisions. Module 5, we cover the conservation of energy. Here we investigate interacting masses, masses that are colliding. So consider a 2 kilogram mass moving to the right at 1 meter per second, and a 1 kilogram mass moving to the left at 3 meters per second, and they're on a collision course. And let's assume that the surface is frictionless just to make things simple. They're going to collide and bounce off each other. Which way is the 2 kilogram mass moving after the collision? How fast is it going? What about the 1 kilogram mass? What is it doing? For this, we need conservation of momentum. To get the final speeds of the blocks, let's imagine a spring on one of them. When they collide, the spring is going to compress. Exerts a force of kx. It pushes on the 2 kilogram block and it pushes on the 1 kilogram block. The force is the same. It's kx in both cases. The compressed spring pushes the 2 kilogram block to the left with the force kx and the 1 kilogram block to the right with the force kx. This is Newton's third law. Every action has equal and opposite reaction. The only purpose of the spring is to see that the force is the same. The only horizontal force on the 1 kilogram block is from the 2 kilogram block. The only horizontal force on the 2 kilogram block is from the 1 kilogram block. Those forces are equal and opposite, and it is kx. So let's write F equals ma for both of the masses. So let's pick mass 1 to start. The force on mass 1 is ma, the mass of 1, times the acceleration of 1. Acceleration, the average acceleration, is the final speed minus the initial speed over the time, over the collision time. For mass 2, it's the same thing. We just use two subscripts. The force on mass 2 is the mass of mass 2 times the acceleration of mass 2. The average acceleration of mass 2 is v2 final minus v2 initial divided by the collision time. The collision times have to be the same. We've already seen the forces are equal and opposite. F1 equals minus F2, or F2 equals minus F1, either way. From this, we can write ma equals minus ma. For each mass, we can cancel the t's, and we can collect the initial terms and the final terms. We put all the initial terms on one side and all the final terms on the other side, and we get m1 v1 initial plus m2 v2 initial. The initial mv's equal m1 v1 final plus m2 v2 final, the final mv's. This is momentum. Mass times velocity is momentum. The total momentum before the collision equals the total momentum after the collision. Momentum is conserved. We derive this equation only in one dimension, but it's a vector. The direction of the momentum vector is the direction of the velocity. We use P for momentum. Who cares? You don't have to know that. You never really use it. P equals mv. The momentum vector P is the same direction as the velocity vector. If they're colliding in one dimension, the appropriate sign for the velocity must be used. If we define positive to the right, the 2 kilogram mass has a speed of plus 1 meter per second, and the 1 kilogram mass has a speed of minus 3 meters per second. So let's make a few points about momentum. There's multiple forms of energy. We have thermal energy, we have potential energy, gravitational potential, elastic potential, we have kinetic. There's only one form of momentum, it's mv. You can't lose momentum to anything else. The only expression for mv, for momentum, is mv. You can't lose momentum to thermal energy. Momentum and energy are completely different concepts. They have different units. They are conserved independently. To test the students, if the students understand the concept of conservation of momentum, I pose this question. Here's a bomb. It's going to explode. It explodes into 3 pieces. There's no momentum before the explosion. Everything's at rest. Each of these pieces has momentum. Where did the momentum come from? Think about that. It's not the chemical potential energy inside the bomb. The momentum of a closed system can't change. If the momentum before the explosion is 0, the final momentum must be 0 as well. And as soon as you realize that momentum is a vector, you can see that if you add the three momentum vectors, they can be zero. There's no final momentum. There's different directions. It's the kinetic energy of each piece that came from the chemical potential energy of the unexploded bomb. Energy is a scalar. There's no such thing as energy in the x direction, energy in the y direction. Momentum is a vector. So back to the problem at hand. We have two masses colliding. If we apply the conservation of momentum equation to solve the problem, we're going to have two unknowns, V2 final, V1 final. But we only have one equation, momentum is conserved. We need another equation. We need some more information. We need information about the elasticity of the collision. Is thermal energy generated during the collision? If it's perfectly elastic, no energy is lost to thermal energy. I don't like that word lost. We should say transferred. No thermal energy is generated. The kinetic energy is conserved if it's perfectly elastic. If it's inelastic, you have to have thermal energy. And if it's perfectly inelastic, then they stick together. So let's do both extremes. Perfectly inelastic, sticking together, and perfectly elastic, no thermal energy is generated. So we'll do inelastic first. They stick together. We're going to take away the spring and put some pine tar there so they stick together. Now we have our second equation. V1 final equals V2 final. They stick together. They're going to have the same final speed. So with the momentum before the collision, we go mv, mv. I remember to put the signs in, and we get minus 1 kilogram meters per second. It's 1 kilogram meter per second to the left. That's the initial momentum in the system, and that must be the final momentum in the system. After the collision, they stick together, so the total mass is 3 kilograms, and we have V final. And we can set the initial speed, the initial momentum equal to the final momentum, and we can divide by 3 kilograms and get the final speed of the combined masses. It is minus 1/3 meter per second, so it's 1/3 meter per second to the left, like that. The common part B to problems like this would be how much thermal energy is lost. What percent of the thermal energy, of the kinetic energy is lost? Well, the initial kinetic energy is that. We can plug in the numbers, 2 kilograms, 1 kilogram, 1 meter per second, 3 meters per second squared, and we get 5 joules. So before the collision, there's 5 joules of kinetic energy. After the collision, 1/half times 3 kilograms times 1/3 meter per second squared, that's 1/6 of a joule. So we started off with 5.5 joules, we ended up with 1/6 of a joule. Almost all of the kinetic energy was transferred to thermal energy. The ratio is 1 out of 33, so 30 seconds of the kinetic energy became thermal energy. This is typical when masses coming together collide. So now let's assume that there's no thermal energy generated. The collision is perfectly elastic, kinetic energy is conserved. So in this case, the second equation is KE initial equals KE final. So now we're back to the situation, 2 blocks about to have a head-on collision. If you have a good spring in the real world, you can make it nearly perfectly elastic. So we're going to set the initial kinetic energy equal to the final kinetic energy. There's that equation. Conservation of momentum is this equation. We have to get the signs right. In the conservation of momentum equation, in the energy equation, you don't because you're squaring the speeds. So let's solve for V1 final. This is the momentum equation. We're solving for V1 final. We put M1 V1 final on the other side, and we divide by M2. Divide by M1 like that. We can take the first term, get rid of those M1s, and now it looks like this. We can substitute this back into the kinetic energy equation, like this. This here is V1 final. We cancel the 1/2s, simplify it. Let's FOIL out this term and hope something good happens. It's going to get messy, I think. So this middle term is this, and we're going to have to square this out. Looks like that. We have to put this back into this is just this term in the square bracket. So we have to put this back into the conservation of energy equation. Now it looks like this. So we were hoping something good happened, and it doesn't look like anything good happened. This is going to take me a few pages. You might want to go get a cup of coffee or something. Fast forward. So we're going to need more space. Let's get rid of that figure. We cancel the M1 V1 initials, multiply both sides by M1 over M2. That gets us this. Remember, it's always a good idea to remember what you're trying to do. We're trying to solve for V2 final. It's the only unknown in this equation. It's right here, it's right here, and it's right here. We're going to try to get we're going to collect these V2 final terms. So this is just rearranging, collecting those terms, factoring it out. This term doesn't have any V2 finals in it. Here's a V2 final, here's the V2 final squared. It looks like a quadratic. This is the constant term. This is just the initial speeds and the masses. This is V2 final squared. So this is in quadratic form. Ax squared plus bx plus c equals 0. Now I'm wishing I hadn't started this. This is a mess. We're going to use a quadratic on this. Here's the quadratic equation. We plug it in, it looks like this. All right, so let's just mess with this thing under the square root sign. If this thing does not have a nice square root, we're just going to give up. I'm just going to Google it, figure out what it is. What's V2 final when two things collide elastically? So here's the square root sign. I'm going to take that out. This is under the square root sign. See what happens. I'm going to FOIL out this term right here. There it is. I'm going to distribute the 4m1 plus m2. I did that over here. These two terms cancel. m1, m2, v1 initial, v2 initial, plus 2m2, m1, v2 initial, v1 initial. Those cancel. That's good. I'm going to have this term and this term. This reduces to this. And this has a square root. The square root of this is 2m1. The square root of this is v1 initial minus v2 initial. Yeah. Okay. We might have a chance at this. So now that's the square root. So I can plug this thing in for the entire messy square root. This thing has two solutions. There's a plus minus here. If we use the negative, we get this. V2 final equals V2 initial. What happens when V2 final equals V2 initial? They missed each other. Of course, momentum and energy are conserved when the masses don't hit each other. Nothing happens. But this is interesting. We have to use the plus sign. And now we get this. And we distribute the 2m1. We get this. We can factor out these two terms and get V2 initial times m2 minus m1. And that's it. That's as simple as it gets. By simple, I mean you can't reduce it anymore. That's the equation for V2 final in terms of V2 initial and V1 initial and the masses. We know what the equation for V1 final is. It has to be everything with the subscripts reversed, because it doesn't matter which block we define as block 1 and as block 2. But let's do it anyway. So if you remember, we had this expression for V1 final from the conservation of momentum. We have V2 final here, but now we have it. It's right here. So we can substitute in this mess for V2 final, and here it is. So we're going to get a common denominator to subtract this term from that term. There's the common denominator. Now we have one term here. There's our m1 plus m2 in the top and bottom. We can combine these terms. Continuing, we get this. Now we need another common denominator for this guy. This V1 initial out front. So there it is. There's our common denominator. And we're left with this. We have minus 2 m2 v initial and plus m2 v1 initial. We can combine those. And we can factor this out. This stays, and we have m1 minus m2 v1 initial. And that's exactly the same as the other one, but the subscripts are reversed. So we did it. So now finally, we're going to try to calculate the velocities after the collision of those two masses. Here's the problem we're trying to solve. A long time ago, we had this. So we're going to call this block 2 kilogram block M2 because it's 2 kilograms, and this block M1. So the final speed is this equation that we just derived, and we can calculate it. Plugging in all the numbers, we get minus 5/3 meters per second. So it's going backwards with 1 2/3 meter per second. The 1 kilogram mag tags it, and it's going to the left after the collision. Now the 1 kilogram block. Here's the equation. We can substitute in the numbers, and we get plus 2 1/3 meters per second, plus 7/3 meters per second. So the 1 kilogram block collides and bounces back. It's going to the right. So now let's confirm that both momentum and kinetic energy are conserved. The initial momentum in the system, we calculated this already. It's minus 1 kilogram meter per second. Now we're going to do the final momentum in the system. We have the 1 kilogram block going positive 7/3 meter per second. We have a 2 kilogram block going minus 5/3 meter per second. That's 7/3 plus, that's 10/3, minus 10/3. 7/3 minus 10/3 is minus 3/3, which is minus 1 kilogram meter per second, and that was the initial momentum in the system, so momentum is conserved. Now, let's conserve kinetic energy because we assumed the collision was perfectly elastic. No thermal energy is generated. The initial kinetic energy in the system, we calculated this already. It is 5.5 joules. The final kinetic energy in the system, we do 1/2 mv squared for both masses. So 1/2, 1 kilogram, 7/3 squared, 1/2, 2 kilograms, minus 5/3 squared, that's 49/18, and 25/9. Need a common denominator here, that's 50/18. We add them up, we get 99/18. Divide by 9, that's 11/2. 11/2 is 5.5 joules, which is the same as the initial kinetic energy. So kinetic energy is conserved. Here's the situation before the collision. Here's the situation after the collision. This is the only situation that conserves both momentum and kinetic energy. The only final condition that conserves both. This was a fun exercise. We're never going to use these equations for V1 and V1 final to solve problems in this class. They're just too mathy. There's too much math, not enough thinking. Too much calculating, not enough thinking. This class is about thinking and figuring things out. And that long process of deriving that equation was fun for me, but we're not going to use it in this class. But it certainly demonstrates that you can conserve kinetic energy and momentum. Ready for lecture 2? Lecture 2 is on two-dimensional collisions. Collisions in a plane that are not head-on, not in a line. So a cue ball in general colliding with the object ball. A collision between two cars that's not head-on. There's a T-bone collision. Curling stones bouncing off each other at glancing angles. And ricocheting.